Welcome to another podcast. In this episode, we're going to be taking a look at the product rule. It's our next rule in a series of rules we're looking at for the derivative. And I want to derive the formula for the product rule with you here, and the easiest way to do this is by focusing on the figure that I have on the screen. I want to know how the green area changes. In other words, how does the area of the rectangle UV, which this represents our product, so how does the product of U and V change as I increase U and as I increase V? So this represents the increase in the size of V. This represents the increase in the size of U. And so I want to know, how does the area in green change? Well, any change that occurs because I'm adding on these elements. And so if you want to think about this, I can think about the change in the product U times V as being the change in the size of the green is equal to U plus delta U. So U plus delta U is the entire bottom length times the new area would be V plus delta V. So basically this is the change in the area of the green rectangle is equal to the new height times the new length. And so if I think of this as I would foiling something, the change in UV is the difference between the new rectangle minus the old rectangle. So this is the new rectangle that's created and its area minus the old rectangle's area. And so if I look at this for a second and look at delta U, the change in U times V, and I FOIL out that right-hand side, foiling out the right-hand side, I get U times V plus, I get U times delta V plus V times delta U plus delta U delta V, and then minus UV. And I want you to take a look at what we get here. The U delta V and V delta U correspond to the blue regions, while the delta U delta V corresponds to the purple regions. And then what basically happens is the UV we had before cancels with the UV we have now. And so the UV doesn't add anything. It's only these changing pieces that add anything to the new area. So basically the change in the size of the rectangle is entirely due to adding up the areas of the blue, both blue parts and the purple part. Now, how does the size of U and V change? Well, if I think of U and V as functions of x, then U and V change as x changes. In particular, I can think of the change of U with respect to the change of x. As the change of x goes to 0, we know that this represents the derivative of U with respect to x. So that's the connection that we're going to make here, and the way I want to look at it is I'm just going to take this equation that we have and divide everything by delta x. So the change of U times V with respect to x is equal to, so the UV parts have canceled, I'm left with U delta V with respect to x plus V delta U with respect to x plus delta U delta V with respect to x. Now, if I then apply the limit as delta x goes to 0, delta UV with respect to x is the derivative with respect to x of the function U times V, and that's equal to U times, I got delta V over delta x, but that's dV dx, plus V times the partial of U with respect to x, or not partial, excuse me, the change of U with respect to x is du dx. And then finally, if you look here, one way to think of this is delta U times delta V delta x. And delta v delta x becomes dv dx, but what happens to the change in u as delta x goes to 0? Well, the change in u becomes 0 if there's no change in x. And so this last piece here is just 0. Because you have both things changing, they sort of cancel each other out. That's kind of the way that you can think of it. And so there's 0 net change to the area of u because both are changing. So thinking about what this says that if you want to write it out, the derivative with respect to x of u times v is equal to u. Typically we write it this way. I'm going to start with the second piece here. It's the derivative of u with respect to x times v plus the derivative of v with respect to x times u. Now that's the Leibniz way of writing it. Oftentimes we'll write it using Newton's notation as the derivative of u and v prime is equal to u prime v, so the derivative of the first times the second, plus the first times the derivative of the second. So all of those are ways of describing the product rule. Now I just want to give a quick example of this. We're going to look at other examples in class as well as in future videos. But suppose I asked you what is f of x, or what is the derivative of f if f of x is e to the x times, let me do like a little polynomial here, x squared plus, let's say 3x. So I want to know what is the derivative of this product. Then for the purposes of this rule, I think of this as being my function u, and this as being my function v. And so the derivative states that I should write down u prime. So I should take the derivative of e to the x times v plus I should take u, which is e to the x, times v prime, which is the derivative of v. So if you'll allow me, I'm going to do this above the equation here. The derivative of e to the x is e to the x plus, here we have another e to the x, and the derivative of x squared plus 3 to the x is 2x plus 3 using power rule there. So sort of a last step here, if I factor out the e to the x because both terms have it, what I'm left with here is x squared plus, I've got a 3x here and a 2x here, so it's plus 5x, plus I've got a constant 3 here. So as a solution, this represents the derivative of e to the x times x squared plus 3x. And so this is the basic idea behind applying the product rule. Like I said, we're going to look at it more in class, and we're going to do more examples with it coming up. But I just wanted to give you a basic introduction to the product rule and explain where the rule comes from. All right, thank you for watching.